Okay, hello everyone to the last talk of the afternoon session. Now I see Rafael YUNIS just connected. So Rafa, if you can please share your slides.
Can you hear me? Can you hear me well?
Okay, Rafael, so you can start.
Okay.
At least please share your slides and I think everybody else can hear you.
Okay. Let me see if I can set to share my slides. Share.
Yes, but
okay.
Yes, now I can see your slides.
Okay, perfect. Yes, it is strange for me too. I can only see you as speaker, Carlos, but even though my volume levels seem to be okay, I don't see myself speaking, you know. So I don't know. But okay, anyways. Shall I start? Okay, I will start. The topic of my presentation here is about fermionic dark matter and self-interactions. My name is Rafael YUNIS. I'm a recent graduate at La Sapienza University of Rome. I will talk about a few novel approaches on these subjects and a few future probes, mostly dealing with the topics of my PhD done under the supervision of Dr. Carlos Argüelles. So, as you well know, cosmology is the study of the universe origin and evolution on its larger scales. The dominant model in cosmology is lambda CDM, which is comprised of galaxies surrounded by halos of cold dark matter, which is cold, heavy, and made of non-interacting particles. This is the basic assumptions of lambda CDM, a small velocity dispersion on the CDM particles. Now, our work has been motivated by recent tensions between theory and observation on CDM. I understand that maybe this has been the topic of a few past presentations on this encounter. I will simply briefly touch on a few of them, such as missing satellites, too big to fail, core cusp, etc. The main takeaway I want to have from here is that these involve a small scale. This involves the inner structure of small dark matter halos, the amount of substructure in the observable universe, etc. For example, missing satellites involves the lack of observation of the predicted amount of satellites in lambda CDM. Core cusp involves some discrepancies on the inner dynamics of small dwarf halos, among other recently observed tensions in lambda CDM. While these tensions can be resolved, first of all, they are obviously a subject of debate. Matteo's talk dealt quite a lot on that from the point of view of the Lyman alpha observable, but also there are many other ways of dealing with these tensions within the lambda CDM model. But this has obviously sparked some interest in relaxing a few assumptions about these dark matter models in general. One of these assumptions can be found in warm dark matter models. These are characterized by lighter particles and cold dark matter that are produced while they are still relativistic. They are produced while their velocities are still highly relativistic. But unlike other relativistic relics, such as neutrinos or photons, they become non-relativistic before the universe is matter dominated. This causes them to, while being non-relativistic today, to still have a significant amount of initial velocity dispersions. This has the effect of having a certain suppression in the power spectrum, a plot we can see here, where we compare the CDM partition in black with several warm dark matter models, a certain suppression of the power spectrum at small scales. suppression in the amount of structure formed at a given scale. For example, here you can see suppression under 10 inverse megaparsec, on 10 inverse megaparsec, which would be 0.1 megaparsec scales. So this has the effect of having less small scale structure, which will alleviate some of these missing satellite tensions. And it can be seen, you will hear more from Carlos, obviously, but it can be seen that these warm dark matter halos actually work best at small galaxies. For example, rare models or more cored models that can solve certain tensions in the inner dynamics of galaxies, such as Corcus. These models are characterized by free streaming, by a process of free streaming. This free streaming scale in these models can be for a particle mass over 50 keV under 10 to the 5 solar masses, i.e. Structures with masses smaller than 10 to the 5 solar masses are, its production is heavily suppressed in the nonlinear universe. So based on some strong observational limits on warm dark matter particles, we focus ourselves in studying a few extensions to warm dark matter. For example, we assumed dark matter self-interactions. These are based on several well-studied extensions to CDM, which we have heard before in this encounter. These imply adding elastic collisions between dark matter particles. These collisions are do not change number of particles. They are simply elastic interactions measured by an elastic cross-section sigma that can have the effect of prolonging the kinetic equilibrium of the species. So we added these self-interactions, these well-studied self-interactions into warm dark matter models. And we named these new models as self-interacting warm dark matter. We presented this model and discussed some few initial X-ray constraints in this paper right here. Now, adding self-interactions to warm dark matter can have significant effects in all sorts of cosmological aspects, from dark matter history, solving tensions with respect to warm dark matter, which we have mentioned, significant effects in halos and substructure, and interesting consequences in the cosmological evolution of the universe. We will focus on these latter ones, which would involve the early universe production of these particles, evolution of perturbations, and the structure formation observables. Now, to start with the cosmological description of these models, we need to consider how warm dark matter perturbations evolve in the early universe in the presence of self-interactions. Now, perturbations in warm dark matter are usually treated by expanding the perturbed Freeman-Robertson-Walker metric that you can see here, including this metric into the Einstein equations, and including for warm dark matter particles an extra equation to describe the evolution of the energy momentum tensor perturbations in the Boltzmann equation. The addition of self-interactions takes place in this Boltzmann equation itself by adding an elastic collision term in the right-hand side of this equation right here. So these collision terms typically have a relatively complicated expression. This is a 9-dimensional integral. It's obviously very important to reduce it for the sake of calculations. Also, this rather complicated expression already assumes that the collisions are elastic and that we are neglecting quantum effects. And we perform this work right here when we reduce this form, assuming an ansatz for the interaction amplitude. We assume a second-order polynomial in the Mandelstam variables. This is exact for most massive mediator models plus some others. This assumes that the interactions are basically almost point-like, being able to be described by a tree-level Feynman diagram, and that we are not adding like others, say, for example, potential effects or charge screening and things like that. This reduced form is based on integration kernels. For example, here you can see the expression for the first order perturbations. This expression is based on these two kernels, G and K. It is important that this expression does not make any assumption of mass. It doesn't assume that the particle is either relativistic or non-relativistic, which is relevant for the case of quantum matter. And all of the information in the model, the mediator, the interaction strength, etc., are encoded in these precomputable kernels G and K. We mentioned it before that the answer is exact for several massive mediator models. For example, this massive scalar model, a form fermion interaction, a vector field interaction with a massive mediator, among others. Now, typically, for the sake of calculations, one does not deal with the full collision term, but instead approximates this collision term further via operator replacing. One, based on the fact that this collisions drive the distribution function to equilibrium, one can assume that any distribution function will approach an equilibrium form in a time given by the strength of the interactions. This time is known as the relaxation time, is typically of the order of the time scale of the interactions. Now, this time scale of interactions can be relatively straightforward to estimate based on these kernels we calculated before. Here we have this expression for the inverse of the relaxation time, the interaction rate, based on the G part of the kernels that we presented in this paper right here. And we can include this relaxation time in order to solve the new perturbed Boltzmann equation. This slide deals with the Legendre expansion of the first order Boltzmann equation. What you need to know is that it only involves adding a relaxation time to the right-hand side of the first order Boltzmann equation and performing the solving of the Boltzmann equations on the same way as it would be for Warner matter. Now, we have an interesting phenomenon when we start dealing not just with the back perturbations, but also with the background. Now, the zero order Boltzmann equation, while it's more relatively simple, we won't calculate it explicitly, but we will focus on a few phenomena relating to statistical equilibrium of these functions. For example, the phenomenon of decoupling. One might know the phenomenon of decoupling for production of typical WIMP cold dark matter. In that case, the coupling is both chemical and kinetical. So the particles are produced by being in thermal equilibrium with the background. And at some point, these interactions become less relevant, they lose equilibrium, and they freely expand. In this case, the situation is slightly different because self-interactions are only able to preserve kinetic equilibrium, but not chemical equilibriums. This is to say the number of particles for this species is fixed, but it still remains in an equilibrium distribution thanks to the effects of self-interactions. And based on the interaction constant of these self-interactions, it is even possible to have this kinetic equilibrium until quite late on the universe history. In fact, it's almost possible to prolong this kinetic equilibrium almost until matter domination. Now, this decoupling effect, this kinetic equilibrium, is maintained roughly while the interaction rate is able to overtake the expansion of the universe. If the interaction rate is higher than the Hubble expansion rate. If this is true, then this distribution function is able to maintain equilibrium. When this fails, this distribution function is frozen in the last value it has and simply freely expands with the universe. A very distinct change in behavior can be seen for this species based on a single condition. If the decoupling happens while the particle is relativistic, say in the earlier phases of the radiation-dominated era, or while this particle is non-relativistic in the later phases of the radiation-dominated era. If this happens early, the evolution of the species is very similar to ordinary matter, but if this happens after the particle became non-relativistic, we have an interesting new situation in non-relativistic self-decoupling. We name it non-relativistic self-decoupling. Here, for example, you can see a plot of where exactly this decoupling happens. In blue, you can see the Hubble expansion rate, and in green, for example, you can see the interaction rates based on a few parameters. And when these two lines cross, obviously, the self-interaction decoupling is had. In this case, as it's to the right of T equal M, then it's non-relativistic self-decoupling. So what's interesting about this non-relativistic self-decoupling is that the distribution is maintained in equilibrium, but the equilibrium itself shifts from relativistic to classical. So the whole background distribution shifts from a relativistic form to a classical form at when the temperature of the background equals to the mass of the particle. Since this equilibrium is kinetic but not chemical, a bunch of conserved quantities are maintained. For example, the number density, the energy density, the pressure, etc. And in this paper right here, we calculated a few of the consequences of this scenario in linear cosmology, such as the distribution function today, a few transition approximations, reduced forms for the interaction rate, etc. And we turned to a numerical application of this approach. We implemented this self-interacting model matter theory in class, which is a C public code for cosmology perturbations. We added this effect of self-interactions with a collision term. We added the effect of tight coupling approximation to avoid stiffness in the system. And we added a whole bunch of logic to deal with non-relativistic self-decoupling. So we are interested in the results of this for dark matter structure formation. So we are taking a look at the power spectra. Here you can see the power spectra on the top panel and the transfer function with respect to warm dark matter in the bottom panels for two different self-interacting models with stellar neutrino models, just for the sake of putting an example, with 1 and 10 keV particle masses and increasing interaction constant. So we can see that while the coupling happens while the particle is relativistic, then the results are very similar to ordinary matter. But on the dashed dotted lines, where the coupling is now non-relativistic, then we have rather interesting behavior. We have a significantly colder spectra, and we have an interesting effect of some oscillations resembling, these oscillations are had because the system retains equilibrium for a rather long period of time, which makes it behave like a fluid and have a distinct pattern of oscillations. These oscillations are common to various systems where the dark matter retains some form of equilibrium, for example, ethos with dark acoustic oscillations, or other fluid-like models for wonder matter, among others. I can't name more than a few right now, but this phenomena is it's well studied in the literature, and there are a few promising probes for the effect of these oscillations, of these dark oscillations in the power spectrum. So first we compared these linear theory predictions with a few observables. Now, obviously, the amount of observables that can be had without going into a full n-body simulation of the nonlinear evolution of perturbations is rather limited. because, well, obviously most of the observables we have today are deeply into the nonlinear regime, so it's necessary to make a simulation for this nonlinear evolution. But still, we can have a few predictions only using the observables from linear theory. For example, with the theoretical pressure mass function, we can estimate the amount of substructure for surrounding the given structure. For example, dealing with the tension of missing satellites. We can also have a certain estimation of how Lyman alpha observations are going to turn out. For the ones that haven't been here yesterday, Lyman alpha observations are absorption lines of neutral hydrogen at high redshift, which can be a rather excellent small-scale probe. Instead of dealing with a full hydrodynamic simulation, we went with the approach of this paper, Murgia et al. 2017, which is making an estimator with the linear theory power spectra that measures the deviation of the power spectrum with lambda CDM. And based on a certain criterion, we can exclude a certain class of power spectra that are, say, too suppressed to be consistent with observations. Here we have the results of this analysis. In the upper panel, we can see the number of satellites to a Milky Way type galaxy. We have here a lower limit on the estimated number of Milky Way satellite galaxies. Well, obviously here we plot the number of satellite galaxies with respect to the mass and the interaction constant for a vector field mediator. We also have an upper limit on this parameter space based on bullet cluster observations, basically corresponding to a cross-section of 0.1 to 1 centimeter square over gram. And we can see a very interesting break around here, which is precisely the transition between relativistic and non-relativistic self-decoupling. We can see that obviously the power spectra become colder, the amount of substructure increases, and basically all of the, at least the Milky Way satellite substructure bounds basically disappear from the parameter space. What can be a bit more informative is the lower panel, that the Lyman alpha NCDM deviation magnitude. We place an upper limit on this deviation magnitude based on a thermal Warner matter model with 3.5 keV mass, which gives you a deviation of about 0.38. We say that every model with a deviation higher than 0.38 should be excluded by Lyman alpha observations because it is too suppressed in order to make the observable features of the Lyman alpha spectrum. So this has been obtained in a paper by Matteo Viel and others in 2013. So we haven't talked too much about particular models of Warner matter, but here I will mention one, NuMSM, sterile neutrino Warner matter. These are sterile companions to standard neutrinos that are produced while in a non-equilibrium processes near the quark hadron transition. This is, or at least was, a rather common Warner matter model that could deal with several tensions in like more common thermal Warner matter models, but has ultimately had quite stringent parameter space constraints. In fact, here we can see the main two parameters of this model, the lightest sterile neutrino particle mass compared with its interaction strength, its mixing angle of sterile neutrinos to active neutrinos. I'm not going to go too deep into all of these constraints. I'm just going to mention the Lyman alpha ones. The Lyman alpha ones, here you can see the dotted line in red, almost exclude the entirety of the parameter space for this model in the non-interacting case. But if we include the effects of self-interactions, if we allow a self-interaction with, say, for example, the maximal allowed amount of interaction strength, we have seen that these power spectra become consistently colder. Thus, the bounds, the constraints on wonder matter models become much less stringent. In this particular example of a wonder matter model, we can see that this red dotted line right here moves all the way to the left to this green one right here. You can see how many more models are allowed by adding this effect of self-interactions. And this is not even getting into the possibility that these self-interactions can alter or enhance production mechanism for these particles, which is something we didn't deal about, but it's an interesting topic for future work. So here I'm more or less nearing the end of my discussion, and I wanted to discuss a bit more heavily about some future prospects for these sort of classes of models. There are several observables that can provide interesting probes for these models. Now, this is a quite well-studied topic, of course, but for example, for 21 centimeter observations and future Lyman alpha observations, they can be a very interesting probe for these small scales. This, for example, these 21 centimeter observations are upcoming data of the 21 centimeter hydrogen line at really high redshift between 10 and 30. This would be very, very sensitive at small scales and with 300 inverse megaparsec scales, for example, and it would not only be really sensitive to suppression in the power spectrum, but also to the possibility of dark acoustic oscillations. I have mentioned that several models of dark matter, for example, some models of cold dark matter interacting with dark radiation, have a strong feature of dark acoustic oscillations, and as we have seen, this model also has these sort of features, and observations like this could be a very interesting probe for oscillations in power spectra that are characteristic of all of these kinds of heavily interacting models in the early universe. For example, the main observable for these power spectral oscillations is the height and the position of the first peak. Now, for the case of, well, for several other models, this has been quite well studied. For the case of self-interacting wonder matter, it can prove to be slightly numerically challenging because these sort of models requires rather high definition simulated data at really, really, really small scales. These scales are rather complicated to compute because they take a long time, not necessarily because of the Warner matter component, even also other more regular components such as baryons or photons, etc., start taking progressively more computing time in these small scales. And on top of that, the self-interacting wonder matter component has to be computed mostly without approximations. Here we can see the tight coupling approximation, the main approximation for this sort of models. This basically has to be taken into account while the interactions are too strong to be solved numerically with the equations we have seen. Instead, we consider it to be a self-coupled fluid, and we don't have to deal with the stiff equation system. But this approximation has an applicability range that is much larger at larger scales. At smaller scales, the range of applicability of this approximation becomes smaller and smaller and smaller, which translates into longer and longer and longer computing time for these modes. So another possible interesting observable for these sort of models is, for example, stellar streams. These are torn or stretched structure by tidal forces, which can have memory of gravitational perturbations by passive structure, as dark scatter slit gaps in these stellar streams. This can be a very interesting probe for the smallest allowed structures on a given cosmology. Say for the smallest allowed halos, that would give us information about whether the real primordial power spectrum is actually suppressed, does have actually a certain amount of small scale suppression or not. This would be very sensitive to the population of the scatterers, but not only to that, but also to their shape and mass that can give us hint about the shape of the scatterers of the dark matter halos themselves. And finally, and probably most obviously, it is very important, and it's already even a work in progress, to perform simulations, to perform embodied simulations, to simulate the evolution of the nonlinear evolution of this cosmology in the late universe, say redshift under 10. It is important to construct these simulations and to not only contrasting these observables with nonlinear evolution, but also validating the existing constraints that we obtained only by linear evolution with a proper, say, honest to goodness n-body simulation. And an n-body simulation can give us several more observables, not just the ones one can get from simple linear theory, such as proper subhalo statistics, history of mass accretion, the possibility of galaxy formation, among a myriad other observables, but I'm sure that you'll hear more about these in future talks. Here, for example, I show some preliminary simulations we have obtained with these self-interacting models, and you can see that for example, the stark difference between, for example, this first top left panel and this top right panel. The top left is without interactions and the top right is with interactions. You can see the considerable increase in granularity when we consider these interactions, when this suppression of the power spectrum is less marked. So I have reached more or less the end. I presented and motivated these halo models. I developed a theoretical framework in cosmology, presented a numerical application, and compared to a few other astrophysical observables. And the key takeaway I want to have from here are the future prospects for these models. For example, the observational stellar streams, 21 centimeter lines, the simulations, the myriad of observables that can be had from these models, and also the future, for example, theoretical or numerical prospects, such as investigated more on self-interacting wonder matter particle production, its assembly history, a better approximation schemes for numerical purposes that would allow us to actually consider more observations, among several other things. Well, thank you very much. I don't know if you have any more questions.
Okay. Rafael, for this talk. And I don't know if people from Pescara have any question. If not, I would like to make a general question. From this framework of class for self-interaction wonder matter, this very general framework, can you, by increasing the particle mass and, for example, putting new terms in the interaction Lagrangian with these dark matter particles, maybe with other mediators or candidates, can you go to self-interacting cosmology similar to the ETOS program with this approach you have shown?
Well, we can have rather similar power spectra to frameworks such as ETOS. You can see here, for example, this is a striking, say, feature of ethos. For example, these dark acoustic oscillations, these are basically the main feature of ethos. Ethos obviously has a few other considerations on the Lagrangian that these sort of models don't have, but still these sort of models might be possibly for a certain given range of parameters of ethos, they might be rather approximate, at least on its features. Say the main takeaway from this is that these dark acoustic oscillation models does not appear only in ethos, but also in these sort of kinds of models. And yeah, basically you can, obviously not with the exact same assumptions from the Lagrangians, but you can have very similar features with this sort of models in the power spectra, in all of the observables that count.
To Rafael for answer. Well, if, let's see if there is any other comment or question. Well, if not, we thank you, Rafael, for this talk, and I think it has been the last talk of this session of Tuesday, and we will start tomorrow at 9 a.m. with the session of Wednesday. Will be the morning session and then afternoon session. So, well, see you then for tomorrow. Thank you, Rafael. And
thank you for inviting, and see you later.